Okay. Good enough. Okay, so I'm going to talk, as I said, a little bit about the architectural trends at the very high end of parallelism, but then also give you some kind of practical information about how to program in MPI. And you know, it would really require more than an hour to give you a complete introduction to either MPI or UPC. So I'm going to give you a little bit of a flavor of what it's like to program in them. If you look at the slides that will be online, there's a much more complete set that give you, more examples than I'll have time to actually go through in this presentation. So I don't remember if anybody talked about the top 500 list so far, but the top 500 list is this competition to figure out what the fastest 500 computers are in the world. And it's measured by a benchmark called the LINPACK benchmark, which is solving AX equals B using LU factorization. And it tends to run pretty close to the peak performance of the machine, at least about 80% or so of the peak on current architectures. And it's updated twice a year to great fanfare. The top 500 list is announced at a conference called Supercomputing in the US, which is in November, and a conference in Europe, which has been in Germany at least the last few years, which is ISC, which is in June. So, and this is the latest data from the top 500 list showing the performance of the machines of the top 500 list. So there's 3 lines here. The n equals 1 line, which is the blue line in the middle, is the performance, the LINPACK performance, the measured performance in this benchmark of the fastest system on the top 500 list. And so you can see the fastest system is over there at about 1.75 petaflops of peak performance. So that's 10 to the 15th floating point operations per second is a petaflop. And you can also see that the performance of these things is going up by a factor of 10. So notice the log scale here every few years. So that's been a historical trend that we're kind of trying to maintain. Now in the number 1 data, the top 500 data, you'll see that there's lots of plateaus. That's because somebody builds a really big computer, maybe worth $100 million or more, and then it takes a while for somebody else to catch up and beat it. But then once that happens, there's often a step function. A much smoother curve is the slowest machine on the top 500 list. There's not nearly as much competition for that slot, but things actually, they kind of, just start on the top and then will move their way down the list until they either get decommissioned and fall off the list, or they end up, near the bottom of the list. So, and those machines tend to be kind of more commodity clusters that people put together, whereas the number 1 machine tends to be supercomputers that are constructed specifically for doing very large-scale computations. The other interesting curve is the sum of all the performance of the machines in the top 500 list. So we're currently at about 28 petaflops of total performance from those 500 machines. And once again, that trend is also kind of a smoother logarithmic curve going up. This is from the 34th top 500 list. It shows where the machines are and what kind of machines they are. So Oak Ridge National Lab has the fastest machine on the list, which is a Cray XT5. It's actually very similar in architecture to the Franklin system that you're using at NERSC if you're doing if you're doing the homework problems using Franklin. It's actually also even probably more similar to Hopper if you happen to use that system. The difference is that we have the Jaguar system has 2 sockets, whereas Franklin only has 1 socket per node. So, and that's as you see, there's about it's almost 2 petaflops of peak performance as measured by the LINPACK benchmark. A number of other machines, so there's a couple of other Cray systems. There's at least one other Cray system on the list. The Franklin system that you have access to is, I think, number 17 right now on the list. We tend to not watch this list very much, especially once you fall off the top 10. We started up here around number 4 and have been moving our way down as other machines come online. So perhaps one of the most interesting systems is this machine in China, which is a GPU-based cluster, and we now see a couple of these sort of unusual-looking machines that are coming online. In fact, there's another one that just came out on the even more recent version of this list. So this is a very complicated architecture that has both traditional kind of x86 processors, Xeon processors, as well as and they're connected by an InfiniBand network, and then GPUs attached to each one. So the big question with those machines is going to be, how do you program them? So it's pretty clear that now that we can construct them, and they're going to be more and more of these machines, I think, available. This is, I think that the top 500 list, I actually don't like it very much because it tends to overemphasize this LINPACK number, which is not a performance number that you typically get on real applications that you care about, that are not doing huge LU factorizations. They may be doing lots of smaller ones or other kinds of computations. But the list is actually very interesting to look at from the historical perspective because it has been tracking the machines on this list over more than 20 years here. So you can actually look at how these machines were constructed. So in the, back at near the beginning, well, in 1993, it was, they were dominated by, there were single processor machines that were still available. And before that, there were even more single processor machines or shared memory multiprocessors, which is the SMP line there. Those were typically vector supercomputers specially built for scientific computing. And over time, you see then the clusters, which are that yellow kind of mustard color there, take off and really have become the dominant architecture. So there's no single processors left on the list because of all the trends you heard Kubi talking about, and instead clusters are really dominating the space. The distinction between a cluster and an MPP can be a little bit difficult to distinguish. An MPP is typically is a machine that has been constructed with a more customized network, not just an InfiniBand or Ethernet network, whereas the clusters will have one of those two networks. So the amount of concurrency in these systems has grown dramatically. So looking at the amount of parallelism in just the top 15 machines in the top 500 list, you see this huge knee in the curve there in around early 2004, and that was, of course, when clock speeds really stopped scaling and in fact slowed down somewhat, and so the amount of concurrency has really picked up, the growth in concurrency on these kinds of large-scale systems. And if you're curious, this is the international map. This was actually using some software developed at Berkeley to show the the weight of the machines in each of the countries. So the U.S. still dominates in terms of the overall performance. What you see here is the size of each of those rectangles is based on the LINPACK number for each of the machines. The number of rectangles associated with each color there is the number of machines that country has in the top 500 list. And you can't really see it since this is just a snapshot, but China, for example, has come from basically nowhere into having close to the largest machine. And a lot of people think that in November, when the next list is announced, that China will probably be at the top of this list. So, to try to give you some idea of why people care about programming and things like MPI, I wanted to tell you a little bit about that trend that we saw, which was cluster architectures and MPPs, which are kind of specialized cluster architectures, really dominating the space of high-end computing. And so this was a report done more than 5 years ago on the future of supercomputing, and it talks about the different platforms and the software and the institutions, the people, and so on. And they identified in this NRC report the idea of an ecosystem that really kind of makes supercomputing or high-end computing work. And so that you have to invest in all the different aspects of computing, not just in hardware. There tends to be a focus on hardware, but really all of these other things play a role. So in this ecosystem, in the early days, in the 1980s, there was a lot of spending in the Cold War spending and big oil putting money into supercomputing hardware, and that was where these vector supercomputers came from. So we got these vector supercomputers that are now considered dinosaurs, and they were programmed with Fortran, vectorizing Fortran compilers, and some, in many cases, third-party applications. So there was the programming model for these systems. So that's kind of what the ecosystem looked like, money coming in to build special purpose architectures, lots of these very powerful machines getting built. Now, in 2006, really the dominant technology was building things out of off-the-shelf processors, so some kind of a cluster, hopefully not quite as decrepit as this picture shows. And so these Beowulf clusters, as they were called, and a phrase coined by Thomas Sterling, really became the dominant architecture and kind of ate into the supercomputing market to the point that you really can't afford to build vector supercomputers today because it was too expensive to build special processors just for a small market, which is still a relatively small market in spite of the size of those machines. So this is where MPI really came to be the dominant programming model, because you can't just take a Fortran application, although people tried, and automatically parallelize it to run on one of these big clusters. So instead, there were actually a number of different message passing programming systems that people were using at the time, and the community recognized that they understood enough about how to program these message-passing machines and what the programming model should look like, that they got together and defined a standard, which is the MPI interface, and that really has become the dominant programming model at this point. So what is MPI, kind of in a nutshell? And I should give my thanks to Bill Gropp, who is one of the people that's been involved in the MPI process from the beginning. So a lot of these slides on MPI I took from him, although I will give my own twist on a few of them. And so it's a library, and so all of the operations are performed with some kind of a routine, a subroutine call. And there's different bindings for different languages. I'll give you a couple of examples in C, but you can use MPI, a header file for Fortran 77 or Fortran 90, and there's also a module version if you want to use that for Fortran 90. So just to start with a really simple program so you all see what an MPI program looks like, we'll create something with 4 processes and just write out their processor number. No interesting collaboration or communication happening in this application. This is basically the hello world of parallel computing. So even to get that far, there are 2 questions that come up when you're trying to write an application. The question is, how many processors are in the world, or how many processors are computing, and which one am I? So there's some code running, and the question is, which processor am I? And that tends to be a very important question to be able to ask when you're writing one of these algorithms, because each processor may have its own unique role within the computation, such as working on a particular part of the computational domain. So MPI com size tells you the total number of processes, and MPI com rank tells you which number you are within, which thread or which process you are within that set of processors. So there's the hello world of MPI, and so a few things to notice. You've got the include file there to bring in the MPI definitions, the interfaces, the MPI initialization statement, which is just tells you kind of how to set things up. And you always have to initialize MPI at the beginning of your application. Then you can get the rank. So here we're asking it to write the rank into this variable rank and getting the size. And then there's the print statement that prints out that you're in a particular rank within the total number of processors. And then at the end, you need an MPI finalize to kind of clean up all of the MPI stuff. Okay. I'm happy to take questions, by the way, along the way if any come up. And so a few notes about these, as I guess I've already mentioned some of these things. We always start and end with it in a finalize. And com world is defined in the MPI, in the standard header file, which is the kind of the set of all, it's the communication set for all of the processes that are involved in this particular job, in the MPI job. So when you launch the job, you get a set of processors. That set of processors is going to be fixed for the run of the MPI job in most cases. And otherwise, there's a and we can then subdivide that into other kind of worlds of communication, which I'll say more about in a minute. So there's I/O that's standardized in MPI 2, not in the original MPI 1 spec, and so in this case we're just doing the I/O with a print statement. But typically in a real application where you're doing large volumes of I/O, you want to do parallel I/O, so you want to use the built-in I/O features in MPI, not just write print statements out. If you find yourself in an application, for example, opening a file from every one of the processes in MPI and writing data out to that file, you'll find that the code tends to not scale very well because of the way it's interacting with a file system. Okay. And there's sort of standard ways to run your applications, and I think that you'll hear a little bit more about that from the TAs, the GSIs, when you get to the hands-on lab. Okay, so not a very interesting MPI application so far. The kind of bread and butter of MPI are the send and receive statements. There's a number of different varieties, but we need to sort of understand some of the details, so that this was kind of what everybody agreed on when they started the MPI design process, interface process as well. You need to have send of data and receive of data. So what else do you need? You need to know how you're going to describe the data. You're going to give a pointer to it. You say how big it is. Can it be a data structure, a more complicated data structure like a linked list? How will the processes be identified? So how do you know that you're sending from 0 to 1? How do you recognize that you're receiving the data from a particular place? And then actually probably the most subtle question is, what does it mean for the operations to complete? So you send the data. Do you sit and wait for the data to be received on the other side? Or does that data kind of go off into the network and you never know whether or not it's arrived at the other side? So, so in order to get some handle on the naming the processes, you first of all have to have, you've got to have a namespace for those processes. And you already saw the idea of MPI rank, but you can get more sophisticated by building up a communicator. So communicator is something that is a group of processes and also a context. And probably the easiest way to think about context, which you won't really run into, I think, in your first MPI application, is if you're writing a library, you want to be able to talk about the MPI stuff that's in that library call, and so that becomes the context. And so you can name this thing, which is a kind of a data structure with an MPI, as a communicator that tells you what processes you have and what context those processes are running in at the given point in time. And so, and then a process within a communicator is given by its rank. The COM world is one of these communicators that's defined by default as all of the processes in the system. And so simple applications are just going to use MPI COM world and not worry about dividing up into other communicators. But this is the more general sort of case. Now, the question about what the data looks like from generally speaking, when you're sending an MPI message, what you're doing is you're sending a bunch of bytes across the network. And it's your job as a programmer to worry about what you put into those bytes, that kind of array of bytes, and then how you interpret it on the other side. And it's a big source of errors in MPI applications that you're packing up a data structure if it's a complicated data structure, and you have to unpack it on the other side, and you've got to make sure that that pack and unpack code is working in exactly the same way to recognize what each byte actually means. So it's not a very this is not rocket science to try to write this kind of code, but I do remember one of my graduate students a number of years ago who had been writing message passing code actually in other libraries, because it was kind of pre-MPI at the time. At about his 5th year of graduate school, says, I do not want to write another pack and unpack routine. So it's not hard, it's just really tedious, and you have to get it right. So MPI defines a set of data types to try to make it easier to try to let MPI do more of the packing for you. And there's MPI functions that you can use to kind of construct these more complex data structures. But the basic data types, you tell it that MPI is sending an int or an MPI double, and that tells you something about what the message looks like so that it's understood by the MPI layer. And so there's all these other kinds of types that you can use in there. But fundamentally, what you're doing is you're packing up information, unlike a strongly typed language that if you're used to programming in something like Fortran or even in C++, where you have a very rich set of data types in the language, you're kind of squashing them down when you get to MPI and sending just the data. There's a notion of a tag, which is also used you can put tags on messages to make it easier to figure out which message is being sent, and you can use an any tag as kind of a wild card to figure out if you want to match a receive operation with any of the incoming messages. So the basic the simplest kind of MPI call is a send-receive pair. So this is spelled as shown there on the slide, and MPI send gives you the start address and the number of data elements that you're going to have, and then the data type of those elements. So you are encoding, it's basically saying it's an array of data of a certain data type that's that has size count in there, and then there's a tag that you can use to match on the other side, and the target process is given by the destination, and then and when this function ends, this means that the data that's the buffer, which is sitting up there in A, so you've got A of the 10-element array A that's starting at the address at the beginning of A. When that data, when this function send returns, it means that the network is all done with that data. You're now safe to go and scribble on that data and not worry about whether it's going to corrupt the message that just got sent. Okay? So this is where the question of completion becomes a little bit tricky. And what that means is that this processor is sitting there and waiting. When you say send, it's going to sit there and wait for the data to do something else so that you can scribble on the data later and not worry about it corrupting the message. MPI receive has sort of a similar set of arguments there, kind of the analog, because you've got to have a place to put the data. So the receive says, where should I put my data? So this is going to wait for the matching send operation, the source and the tag operation, and So the source gives you the process ID and so on, and then this is going to, it's going to have a status that has some other information like the size of the message that comes through. So those two things, the MPI send and MPI receive, these are the blocking versions, which means receive is also going to sit there and wait for the data to come in. Okay, very simple program with MPI send and MPI receive. This is, so you see the initialization statement there. Once again, getting the rank out of it, and here's process 0 sending to process 1. So it's just a toy program with just two processes, and they're sending just this data 1, 2, 3, 4, 5, 6 from process 0. So if your rank is equal to 0, then send it, and if your rank is equal to 1, then receive it, and then you print out that you received it, and then do the finalize and return. So as I said, just a toy program, but you know it's not a very sophisticated concept to do the send and receive. What you'll find in MPI applications is the complexity then goes in figuring out exactly how you put the data structures together and making sure as you send more complicated things that they get packed together and unpacked correctly on the other side. There's lots of other versions of these different kinds of send and receive operations. There's also the other thing that's very popular in writing MPI programs are what are called collective operations. So so the collective operations are named collectives because it means you're getting all the processors together to do a particular operation. So the simplest examples are broadcast and reduce. So when you do a broadcast, it says all the processors are going to get together. One of them is going to send data, and all the others will receive the data. And MPI reduce is just the opposite. It says all the processors are going to get together. They're all going to contribute some data value, and they're going to somehow get combined into a single value that's going to live on one of the processors. There's other variations on this that combine broadcast and reduce together, so you can reduce everything and then broadcast it back out again all in one call. And the reduce, though, has to have some function that it's going to use to combine things, because you're taking in, let's say, floating point numbers, and you have to figure out what to do with them. So you can do a sum, you can do a product, you can multiply them together, you can take a minimum or a maximum, and so on. And there's other things that you can build in. So in a lot of numerical algorithms, you can actually use the collectives, that is broadcast and reduce, instead of send and receive. And in many cases, on a well-optimized MPI implementation on a machine that is also, like on a supercomputer like on Franklin, where Cray built the MPI library, at least optimized the MPI library, it is often the case that the collectives will run faster than you building your own collective out of send and receive. So in particular, when you do a broadcast, if you're doing a broadcast to 1,000 processors or 10,000 processors, you don't want to do that by having one processor just do send, send, send 10,000 times. You want to build a tree. And so there's tree algorithms. They're not always binary trees. They may be other kinds of trees that are, tend to be, that they have tuned and have found are optimal for a particular kind of machine configuration or a particular size of the data that's being broadcast. And so you want to reuse that effort that somebody has done to make the collective operations go fast. Now that said, it's not always the case that the collectives are more highly optimized than send and receive. But typically you want to try to use those higher level constructs. It makes your code more readable, and it makes it, and usually it'll make it run faster. But sometimes you'll find non-scalable parts of an MPI implementation, especially if you run on something more like a Ethernet cluster without a well-optimized, an MPI implementation that's specifically tuned for that architecture. Some of the MPP systems, the supercomputers that are built as these clusters but with custom networks, so something like the Blue Gene system, which was one of the machines in the top 5, actually two of the machines in the top 10 of the top 500 list, they have a special network that helps them run the collective operations faster. And so that's another good reason to use the collectives. Here's a simple example of a program which is to compute as a kind of a Monte Carlo simulation of computing pi by computing random numbers and determining whether or not they're inside the unit circle. And so you're just, there's kind of the usual startup stuff in here, and there's a broadcast statement just to see the syntax kind of in practice. And there's a reduction then to add up all of the number of hits that are, you're kind of throwing these darts at a unit circle. You're figuring out how many of them end up inside the unit circle. There's the little computation that's checking to see whether or not where these random numbers are falling. And then so you add all these together and then compute the approximation for pi that way. So just a simple example with broadcast and reduce in them. As I said, there's also, by the way, versions of this example written in Fortran and C++ if you look at the online slides that I just didn't want to show you even more syntax today. So in terms of all of the collectives, there are a lot of different collective routines, gathering things together, vector versions, which are taking large chunks of data and doing that, scatter versions that are spreading it out, where each processor gets a different set of data, which is different than a broadcast. And there's all what are called all versions. So you'll see all in front of these, which means that they are delivering the results to all the participating processors. So an all reduce, as I mentioned before, is an example where you're doing a reduction and then broadcasting the result. And there again, the implementation can often do that. It should be able to do the all reduce faster than you can do a reduce followed by a broadcast, because it can combine, as it's sending things up and down these trees, it can combine the messages inside there to give you an answer more quickly. And then the V versions allow, I should say, chunks of data, I think, but anyway, hunks of data to have different sizes. You can say that you're gathering up data, and each process that's involved in the collective operation is sending a different size of data. We're actually in the middle. In fact, I meant to mention a little bit about MPI 3, but MPI 2 is the latest standard that's in practice that's been implemented, and it has a couple of extra collectives that were added to the library of collectives. Okay, so a little bit about understanding MPI applications and the kind of bugs that you can run into. I mentioned the packing and unpacking. Those are pretty easy to understand what's going on there, but you do have to just be careful when you're packing up your data structures that you unpack them the right way. More subtle problems come up because of the buffers, the buffer management that happens in the implementation of MPI. And unfortunately, once you get past writing your kind of hello world and maybe your pi example, a few simple things, you do end up oftentimes having to really understand something about the buffering within an MPI implementation, because it does affect the semantics of how MPI works. So there's some subtleties that come up from the deadlock problems that you can run into, the buffering, as I mentioned, and also whether things are deterministic in terms of the execution. That is, will you always get the same answer every time you run this program, or does it depend a little bit on exactly the order in which messages may go through the network, which may not be the same. A lot of machines do not use deterministic routing algorithms, so messages may actually take different paths through the network depending on other things that are going on in the system at the time. And they can also have a big impact on performance. So when you do a send operation, you've got your user data structure. That was the A array in the example, and I think the other one was a B array on the receive side. So one way of implementing this inside the MPI library is, as soon as the user says send, you copy their data into a local buffer that you as an MPI library writer are managing. That will at some point go into the network and will get picked up on the other side and be put into a buffer. And then when the user on the other side says receive, it will be pulled out of the local buffer and put into the data. Now there's a bunch of points in that description at which what processor is making sure that that happens? What processor is making sure that the local buffer goes into the network, or the data in the network comes out and goes into the local buffer? And so this is a two-copy scheme, which is sort of simple to understand, but can be expensive in terms of the performance, because these copies are expensive operations. They may, going through the network is expensive, but so is just copying data in terms of the memory cost of doing the copy. So it's better if you can avoid the copies. You just take the user data, you send it directly into the network, and then the data comes out of the network and goes directly into the user's data structure on the other side. So this requires, though, that the sender either wait for the delivery, or that it has to return before the send is complete, and at some later point then you come back and say, did my data actually get sent? Okay, so if you're not going to sit there and if you're not going to put it into local copy, then somehow you have to know whether or not the data has gone through the network. So so this can create sources of deadlocks in your applications. So for example, if you want to send a large message from process 0 to process 1, and you don't have enough storage at the destination to send that message, then the sender has to wait for the user to provide the memory space that is going to be available for the receive operation. And you can, just in this very simple example with two processes, both doing a send and both doing a receive, this can cause problems of deadlock because you may not have enough buffer space. So imagine that you only have one buffer for saving each one of your messages. Each process has one MPI buffer. So process 0 says send some data to 1, and process 1 says send some data to 0. They both have one buffer, so they fill up their buffers, and now they can't go anywhere because there's no local buffer on the other side to put the data into. So it's a classic sort of deadlock problem. And so this code, which you can write in MPI, well, with more arguments and so on here, is considered unsafe because it depends on the number of buffers that are in the MPI implementation. One of the things that the nurse consultants do when they're helping people optimize their code or trying to figure out how to help you get the code to work is often to help you figure out how, there are sometimes parameters that you can set in the MPI implementations, or typically are, that will allow you to get either better performance, but also to avoid or create deadlocks depending on the buffer space. So it's kind of an outside of the MPI spec. There's this question about how much buffer space you've allocated to MPI, and it'll be configured in a default way on the system, but in some cases then you can override that. So. So one of the ways in which you can get around this problem is to be more careful about how you order the messages. So rather than having both of the processors send and then receive, you have process 0 send and receive, and the other one receive and send. So you make sure that the send and receive, the first pair, can complete before it's time to send the second one. And you also can make sure you can also use a combined send receive operation, which kind of does these things in the implementation for you. So. Another thing that you can do is to supply your own buffer space for the send so that you're not relying on buffer space that's inside the MPI implementation. This is called a bsend. And so you can say, here's a buffered send, and now I'm going to have an extra argument which tells me tells the implementation what buffer space to use for it. And then the last one, which I think is the most popular, actually is to use what are called non-blocking operations. So these are called iSend and iReceive, what this says is that the implementation will not necessarily send your data out right away. You'll return from the iSend function even though the data has not been received, and you'll return from the receive function even though the data may not have been received. So later you have to do a wait, which is done here with a wait all. There's other variations of wait to determine whether or not the send and receives have completed. And this now kind of pushes the implementation, the scheduling problem of the data movement into the implementation of the MPI library and lets it handle exactly when things are going to get sent and received. So a little bit more about, about these MPI operations. You need to then have some way of, if you want to do something other than wait all, you need to have some way of waiting on a particular MPI operation or a particular set of MPI operations. So these are called request handlers, and you see a declaration of them right there. And then you can, when you do your iSend and iReceive, you name a particular request handler. This is the variable called request. And then you, when you want to wait, you wait on that, which will wait on those the operations that were performed with that particular handle. And so you can also, and then there's also a way of testing this to check the test without waiting. So some other things, you saw the wait all before, and there are also things like wait any, which waits for any of the MPI operations to complete. This tends to be useful if you have done what's called pre-posting receives. So a very common style in a well-optimized MPI application is to post receive, receive, receive as early as possible, then to do some other computation. The sends will come in whenever they come in, and now there may be work that you can do depending on whether any one of those receive operations has come in. So that would be a wait any, or something like a wait send, wait some. It's very important in these MPI applications are called SPMD, or single program multiple data applications for the most part. There are actually variations of this, but most MPI applications will have one main function, and that main function will run on all of the threads. Now they can call different subroutines at different points in time. There's nothing that keeps them necessarily synchronized, but they all start out running the same copy of the code. And and therefore, although you may, the message passing, the sends and receives provide a certain level of synchronization, because when you say wait on a message, or if you send a blocking send and receive, that will synchronize between those two threads, so you know that when that operation is completed. A much more common kind of synchronization is to say, wait for every thread or every process in the world to get to a certain point in the execution, or every process that's within a particular communicator to wait until that processor gets to that point. So the barrier operation will sit and wait until all the processors reach that point. Okay, so MPI has really become the de facto standard. Obviously, I did not try to give you a really complete overview of MPI and all of the details that you would want to know for writing a complete MPI application, but it is enough to get initial MPI code written if you want to try it out in the lab, and you can easily then read about some of the other features that I alluded to in terms of especially things like the non-blocking operations, which tend to be very important in practice, as well as the collectives, and really learn about those things. Now, it's become the de facto standard, which is both good and bad. It's good because what it really means is that applications that you write for one machine typically are portable to other machines at the same time, but also portable to future machines. So you write an MPI application on a machine in 2006, and it still runs on a supercomputer today. There's maybe some amount of performance tuning that needs to happen, or you may find the algorithms you're using are not scalable enough. But the code is, even in spite of the fact there have been multiple versions of MPI, that code is, for the most part, portable across those different versions. The other advantage is that it really separates the language that you want to program in from the communication mechanism, the library. So if you prefer to write in Fortran, you can write in Fortran. If you prefer to write in C++, you can do that. If you want to mix the two together, you can also do that. So the serial programming language is really separate from the message passing library. And there are versions of MPI for Python and for Java and for other things. So there really are the most commonly used MPI implementations or interfaces are for C, C++, and Fortran. So the downside of this is that because the dominance of MPI, which has allowed things like Beowulf clusters, these clusters of Ethernet clusters of PCs to become very popular, especially in individual university laboratories, your research group might have one. It's also become kind of the least common denominator for the technology for building supercomputers, because if everybody says all I have to do is run an MPI application, then it doesn't encourage any vendors of HPC systems to try to make networks much faster, to try to build large-scale shared memory machines, or to try to build things that have more interesting kinds of mechanisms in the network. So the truth is that the programming models that we've used for parallel computing really reflect the underlying hardware, the programming model being the languages and the libraries and so on. They don't tend to try to hide the hardware. So when vector computers were popular, people programmed in Fortran. When clusters were popular and are now popular, they program in MPI. So Horst Simon, who is the Associate Lab Director for Computing Sciences at LBL, once said, I'm not sure how they will program a petaflops computer, but I'm sure it will need MPI somewhere, which has certainly turned out to be true today in 2010, or even a couple of years ago when the first petaflop machine. He's also now said the same thing about the next exaflop machine, which is projected, if we do a lot of investment in the technology, that we may have an exaflop machine in about 2018. If you just kind of follow the curves out, that's where it goes, although there's a lot of problems there, the biggest one being power. That if you kind of project those curves out, even taking into account some of the usual technology trends, that machine, an exaflop machine today, if you built it, say, 10 years from now with the technology that seems like it would likely be available if we don't do anything special, would require about over 100 megawatts. And so from my perspective, as somebody who also runs a computing facility, so I'm the director at NERSC, 100 million megawatts, 100 megawatts of power translates to about $100 million annual budget for the electrical bill. So we're not going to build computers that hopefully require $100 million. If you do a more kind of aggressive scaling of the system in terms of the memory technology and everything, you can actually get closer to. I was on one study committee where somebody from Intel stood up and said, "This machine's going to require a gigawatt," and I said, "Well, we might as well just go home because there's no way we're going to spend." We're going to spend that kind of money just powering the system. But I think we've made some progress in terms of the technology to bring that number down. Lots of other references. Here's some of the online web pages for MPI. Here's some of the books for MPI. As I said, these slides will all be online, so you shouldn't try to copy these or anything right now. All right, so I'll spend a little bit of time then talking about my own personal research interest for programming these kinds of large-scale parallel distributed memory machines, which is not in MPI, but actually in using a partition global address space language. And And kind of the key to that is a different communication mechanism that we call one-sided communication. And hopefully I have the slide in here that talks about the one-sided communication model. So we can run, what's wrong with running MPI as we move forward to a machine like Hopper or Franklin? Well, we can run an MPI process on each core. And if I look at the 3,000 users at NERSC, most of them are running an MPI process in each core today of the Franklin system. The Hopper system that we're in the middle of installing, so we're actually upgrading Hopper, and it's going to have 24 cores per node, per shared memory node, 2 sockets, so 12-core chips. This is the AMD Manycores chip. So can we run an MPI process in each one of those cores? Well, you can do it. Certainly the MPI implementation will support that. The problem is that MPI forces you to chop up your data structure so that each processor has its own little piece of the world of the data structure. And there are some parts of the data structure and some algorithms that need to be need to be replicated. So these tend to be things like ghost regions around a grid. If you chopped up a grid, you're going to replicate those ghost regions. Sometimes if you're building you have a large table, and that table is needed by every processor in the system, so you end up replicating that table. So the problem is the amount of memory per core is not growing at the same rate as the number of cores per chip. And so our ability to put an MPI process, which requires that you chop up your data and replicate the parts of it that are needed everywhere, is not going to scale very well as we grow the number of cores. The prediction, by the way, for an exascale system is that it'll have about 1,000 cores on a chip. Exactly what it means to be a core in that time frame is a matter of quite a bit of debate. Are they little things that are inside of GPUs, which I think you'll hear about later today or tomorrow morning, or are they more like the current kinds of cores that we have today, at least laptop, or are they going to be the kind of cores that are inside your iPod, which is one of the ways of getting energy efficiency out of it. So there's a bunch of problems with trying to run MPI. The memory utilization is the biggest one. There is some copying overhead required because even if you run the efficient version of MPI, you at least have to make a copy of the data from the send side to the receive side. Whereas if you have a shared memory hardware and you can directly share that memory, then that's unnecessary to make those copies. Okay, so there are a number of these partition global address space languages. The one that I'll talk a little bit more about is called UPC. And there's a bunch of compilers available for UPC. So this is not just a Berkeley research project. It's actually, there is a project mostly up at LBNL, but partly on the campus, which is an open source compiler for UPC, a bunch of work on compiler optimizations and runtime system optimizations and things for this class of languages. But there are also commercial compilers from Cray, from SGI, and from HP, as well as a open source GCC-based compiler from a small company called Intrepid. So there's lots of different UPC compilers. Sometimes, like on the Hopper machine, we are actually running, and on Franklin, we're running Cray's compiler, although Cray's compiler is actually running on top of our runtime system from Berkeley on the Franklin system. There's another language based on Fortran, which is called Co-Array Fortran, one that really is just a Berkeley research project called Titanium, which is based on Java. And there are a bunch of newer languages that are kind of like these partition global address space languages, but have some more dynamic notions of parallelism in them. They include a language from Cray called Chapel and one from IBM called X10, as well as one from Sun, which I think is still an active project. But there's been continuing, there's fairly large projects associated with Chapel and X10, and those languages you can try out if you want to. There's releases of those software. So let me just give you kind of quickly an idea of what UPC looks like. So the execution model is very similar to MPI in that there's a fixed set of threads, and you can ask things like, what thread am I? You can do barriers between all the threads, and you can ask how many threads are there in the world. And there's kind of a detail here that I won't go into about the compilation modes, because in some cases the compiler, if you tell the compiler how many threads you're going to run on it, can do a better job of optimizing your code, but then your code is really restricted to only running in that mode. And there's certain things you can say in that case as well. So here's Hello World written in UPC. It has kind of the standard, it's got an include for UPC, and then it's got, this is the C version, and so you're using the variables mythread and threads to write out what rank you are, if you will, in the MPI terminology and the total number of processes that are in the program. So here's the Pi example, once again, that I talked about earlier. I should put the picture sooner. So this is what one version of the Pi example looks like in UPC, this is actually doing completely independent computations of pi. There's no communication or sharing in here, so it's not a very interesting program, but you can see the different pieces of it. So any C program is a legal UPC program, and this is the only thing that makes this not a straight C program is the myThread variable there, which is seeding the random number generator with a different number so that each process is using a different set of random numbers. And so each processor gets its own copy of the variables as it would in MPI, and then it can use the same input arguments and so on. So there's a little bit of helper code in here, which is just doing some serial computation to actually do the pi calc to figure out where the random numbers are sitting. Okay, so more interesting is this is the cartoon of what a UPC program looks like, and really what makes it different than MPI. So you have this same idea that you've got a set of processes in the world. We tend to call them threads because traditionally in the computer science arena, when you have processes or things that have a partitioned address space in which they're separate address spaces and you can't access data across processes directly. That's kind of changed a little bit, but that's sort of the traditional use of the word. Whereas threads are things that share data. So if you've programmed in p-threads, Barbara Chapman talked about OpenMP. That's a shared memory model. So what UPC and these other PGAS languages are trying to do is to give you the best of both worlds. That is the ability to directly access variables that live on other processors, but give you some control over how those variables are laid out in the memory space so that you can build a much more scalable machine. The problem with OpenMP is you can only run it on shared memory hardware. You can't run it on 10,000 processors. The problem with MPI is that you're forced to chop up your data structure and not allowed to share any data between any of those processors, even though some of them may be living in the same memory space. So UPC, this is kind of the picture of the memory model. We have variables in it like the hours variable that's declared with a new annotation, type annotation shared, and that is being stuck in the shared memory space. And now any process in the system can read or write the variable hours, whereas the variable mine is replicated on in each one of the process thread spaces. So now we can use this to rewrite the pi example. We've just created a shared variable hits inside of here and done, and everybody's incrementing to them. Now, this has some obvious problems. It's going to have a race condition in here because all the processes can be incrementing this hits variable at the same time. And in particular, what could happen is some of the updates will get lost. So this is not a correct implementation, but it does give you an idea of how the syntax works. There are many ways in which we can fix that. One is to put a lock around that. Not a particularly good idea in this case because there's not much work going on outside of that increment statement, so it won't scale very well, but UPC has locks to allow that. You can also build shared arrays, and these arrays now are going to be spread out over the processors in the shared address space. So this gives you an idea of how different declarations of an array, X, Y, and Z, will be shared. And what you see in red is the element that's stored on thread 0, or the set of elements that's stored on thread 0 in each one of these cases. We call it having affinity because you can run this UPC code on shared memory hardware, in which case it's not actually, it's just stored, the data is stored in the shared memory, but it still has logical affinity with thread 0, which we also find in optimizing even shared memory programs that you often want to have this kind of locality control. You want to have some notion that a certain set of data really has affinity to one thread because it performs better in the memory system rather than having, we talked about cache lines and false sharing and things like that. It avoids having cache lines that move that are shared too much between the different threads. So here's a version that now uses a little array, which is an all hits array, and that is a shared array. So every thread has a different element in it. It's of size threads, and now they're all incrementing their own entry into that array, and at the very end, thread 0 in a very non-scalable algorithm goes and adds up all the hits in the all hits array to calculate the answer, and then only thread 0 then knows the answer and prints it out. You can use a collective there in UPC to make that more scalable. You can use other kinds of algorithms there also to make a more scalable implementation yourself. So as I mentioned, there are locks. There are also collective operations inside of UPC, but I don't want to go into a lot of details. What I do want to do is just tell you a little bit about some of the current things that we're looking at in and kind of the performance of UPC, and to tell you why we call it a one-sided communication model. And I should say that in MPI 3, the current standards effort that's going on, the MPI committee is trying yet again to define a one-sided communication model for MPI. They did this in MPI 2. It never was picked up because there were some problems with the way it was specified, and very few people ever used it, and then very few of the implementations ever optimized it. But what does it mean to have a one-sided message given that you're communicating in both cases? Well, the difference is that a one-sided message has an address and a data in it. That address is something that is understood at the architecture level. In a two-sided message, it's got the same data associated with it, but it has a message ID. That's one of these MPI things. The MPI library makes up a message ID. So when you say send and you say receive, it can figure out what send and receive are, how they fit together. So it may have some information about the process that sent it and the tag and so on. So fundamentally, though, what happens is if that MPI message gets picked up by the network interface on the other side, you send this data out, even with a very smart network interface, like an InfiniBand network or on the Cray network, it can't figure out where to put that data in its final place because all it has is a message ID. And the only way it can figure out where to put the data is to ask the host CPU that's running the MPI application on that side, basically, where is the receive operation that goes with this message ID? Because that receive operation will tell me what address to put it in memory. Okay, so there's fundamentally some information that has to flow. Now, if you're lucky and the programmer has pre-posted their receives, then maybe there's the information, the mapping between the message ID and the location in memory will have been kind of built before the message ever comes in. So there'll be a little match, a tag match that happens in the table, and the data will be written directly into memory. So you're trying to avoid making extra copies of the data. But if you don't have a place to put it, you're going to have to put it, the MPI implementation will have to put it in a temporary buffer and wait for the receive operation to complete. The difference is that a one-sided message has the address, and so when that message gets to the other side, the network interface says, oh, I know where to put this. If you've got DMA support, which is direct memory access support in your network interface, it will just take that data and directly write it into the user-level data structure that it is expected to go into. So it's called one-sided because you're not involving the host CPU on the other side. What you did in the beginning of your UPC application was build distributed arrays or pointer-based data structures so that the other side knows where the data lives on this side when it sends it. And so before it gets there, the data already knows where it's supposed to, the message in some sense already encodes where that's supposed to land. And it gives you actually better performance to do one-sided communication because at the bottom of these networks, they're all doing these DMA operations anyway. And what it's done also, another way of looking at it is decoupled the synchronization of the message from the data movement. So here's one slide just showing the difference in bandwidth that you get from running a one-sided communication layer, which is our layer called GasNet, compared to running a MPI layer. And you can see as the message size varies across the x-axis, there's a substantial difference in the bandwidth that you get. This is pushing data out in the network as fast as you can in this micro benchmark. And, but the GasNet is getting better bandwidth. And that's because you've decoupled the synchronization operation. You're just pushing data out in the network as fast as possible, not worrying about are buffers ready, has something on the other side pre-posted to receive, and so on. And this kind of bandwidth number is true across, these are actually latency numbers. You get somewhat better latency from one-sided communication. Big messages, it doesn't really matter. So typically these numbers are about the same. But for something like a 4 kilobyte message, you'll actually get better bandwidth than from this kind of a flood test. And I'll just say then that you can actually use this in applications as well, things like 3D FFTs that are also doing a lot of communication because they're transposing data, actually run faster because of the one-sided communication. So I just want to end by mentioning that we are looking at how to extend PGAS languages to GPUs and multi-core, many-core processors. One of the things that's coming up on these many-core processors, and particularly on GPUs, is explicit memory management. So explicit memory management at a GPU means you're doing DMA operations. You're saying put data or get data from across a PCI bus and so it's really very well matched to the idea in PGAS languages, which is doing these kind of put and get operations. What we have to do is extend the memory space. And here's a little picture. Let me see if I've got that one. what the memory space might look like on a cluster of GPUs. So on every node, which is called a processor here, you have a CPU and a CPU's memory and a GPU and the GPU's memory. What you want to do in a partition global address space is then allow every CPU to write to any other GPU or CPU memory in the system as long as that data has been declared shared, and similarly on the GPU side. And so we're actually building some runtime support for this and working on language extensions for UPC to give you this kind of a kind of more general or hierarchical partition global address space model. So if any of you are interested in working on this, we have opportunities within the group. Just send me an email, and both on the research questions and certainly lots of implementation work to do as well. And if you're interested in trying it out at some point, this one's not quite ready to try out, but certainly UPC and the other languages, Core, Fortran, and Titanium are available if you'd like to. So with that, I will end and see if there are questions. Yes? Yeah, so I think that, so Andy and I have been in a lot of these meetings together, and I think we're actually on the same page, which is MPI is not going to be the universal programming model on an exascale machine. And I think already with the Hopper system, we're seeing this. I think MPI will still exist in 2020, and I think it will still be used in the applications at the high level. But I think the parallelism that's inside of the nodes is not going to be MPI parallelism. So I think there will still be MPI parallelism, and there will still be MPI. I would like to say, well, as somebody who's been advocating for PGAS languages, that MPI will disappear and UPC and Core, Fortran, and Titanium will take over the world. But I think actually realistically, there's a lot of investment in MPI. And when you look at the architectural models for exascale, it's very consistent with MPI at a course level. It's that you need MPI plus X. And the big question right now is, what's the X? We're looking at UPC as the X, even if you don't think UPC is the thing for everything. Maybe UPC is the right kind of gives you locality control but still shared memory access. Other people are looking at OpenMP and variations of OpenMP, and other people are looking at CUDA and completely different kinds of programming models. But yes.
Maybe this is a very silly question, but in the middle of your presentation, you show us kind of bricks building kind of chart. Click on that.
The one with the top 500 numbers on it?
That's correct.
Yeah, with the U.S. about half of it, and China coming with a big piece of it. Yeah, okay, let's see. I guess I could have done this in a random access way instead of serial, but I will run into it here. There it is. Okay, that one, yes.
My question is, let's see if somebody else try to use that kind of process supercomputer for the, let's see, very different applications, such as maybe Google data center.
Right.
That process computer beat Google's data center computer systems, or very different? I know that's a kind of upper and orange comparison.
Right. So we're looking at this, and I'll tell you why. We have a project at NERSC called Magellan, which is a cloud computing project, and we're trying to answer the question. It's maybe not quite the data sector, but center question, but we're trying to look at the question of whether cloud computing is useful for science. Okay, so we know cloud computing, really valuable model for commercial settings. So what about scientific computing? And the particular piece of scientific computing we're focusing on is not petascale applications where the petascale applications are running across the whole machine. We've actually done some benchmarks on that, and I can tell you that the slowdown that we see, even from fairly modest size applications running on, say, 256 cores between our supercomputer and running on Amazon EC2, it can be up to a factor of 50x slowdown. Okay, so you're really not using the machine. And the reason is it's got an Ethernet network, not an InfiniBand or other customized supercomputer network. It is not scheduled in a batch scheduled way. So these supercomputers are scheduled so that when you say you've got 256 cores, you've got them all to yourself. And it will give you the whole node. So that's, and whereas in Amazon, they're going to virtualize, and they're going to give other people parts of your node, and they may even share your core with you and things like that. So those are the big differences. That said, there's the big challenges that we see as we move forward, are common between the data structure, the data centers and the computing centers. We think of ourselves as a computing center, and the data centers have the same electrical cost problems and the same things that are going to drive them to look at embedded processor cores, very lightweight, low-power cores, as we will. Now, we've got a lot of floating point computations. They may not. So GPUs may be of more interest to us and less interest to them. So there's going to be some. So right now, the way their systems are configured, they're not very well suited to our workload. But actually, Amazon has just come out with an announcement, and SGI had one a couple of months ago saying we're building kind of a science cloud. I forget what Amazon's is called. Maybe somebody else remembers. But they're offering now a cloud with higher speed network. I think it is InfiniBand, high-speed processors, and kind of guaranteed scheduling where you get the whole node to yourself. So, and they're also trying to schedule jobs in such a way that they're grouped together within the network so there's less interference from other jobs in the system. So then it becomes purely a business model. Does Amazon, somebody said, a good way to make a small fortune in supercomputing is to start with a large fortune. So I'm not sure whether Amazon knows how little money they may make in this, right? The supercomputer centers like NERSC and the NSF centers, we're nonprofit organizations. We just have to break even. But that's going to be, I think, the big question is whether Amazon can find a profit in there.
How about the opposite direction? Opposite direction.
In what sense?
If somebody use your supercomputer for data centers,
Data centers.
Is it beat their systems as far as performance?
The software is not architected the right way, I think, to do that. I don't think it's as much of a hardware question as it is a software issue. And we see this already on our supercomputers. There's part of our workload that is lots of small jobs, and maybe even with a workflow where they sort of want to run 10 jobs, and then they want to see what the output is for them and run another 10 jobs. And those kinds of workflows are much harder to run on supercomputers. So the other big difference is we run lightweight kernel operating systems on the compute nodes. They run full operating systems on theirs. And so those kinds of complicated workflows and so on, they want dynamically linked libraries. They want full OS support, multi-threading, and so on. Those tend to work better on a full OS. And the problem with a full OS is it's hard to scale that to 10,000 cores and make it actually perform well. So you tend to try to pare down. So we're now actually on the Hopper system. We're going to have at job submission time, you can pick whether you want a full OS running on your processors or you want the microkernel, because it depends on what your workload looks like. But that, I think, would be the other. It's a good question. It's one I've talked to people at Cray and IBM about a little bit. Is sort of what's their cost? People think of supercomputers as very expensive, but I think it's actually the price difference is, if you look at the total cost of ownership, it's not that big a difference because, yes, they have a custom network. They put a lot of engineers into that to make it run really, really well, and some custom software. But the cost of ownership is largely about the system administration costs, the power costs, all these other things. So that becomes a smaller and smaller fraction. Yes?
About the global
space. Oh, thank you.
Yes.
About the global partition address space, how you figure out what the best memory mechanism if you have shared memory, like you have processes shared in one processor with multi-cores, and then you have shared memory, or processor remotely with other memory address space. And what's the performance advantage over using MPI with MB directly? What the performance? I know it will be harder to implement than using PGAS, but what's the performance benefit?
So we're looking at that, and somebody in the UPC group has been doing a bunch of comparisons, and others are looking at that as well. And I would say right now the problem is the biggest variables are the quality of the benchmark that was written and the quality of the implementation. So we've spent the last 5 years trying to make UPC really competitive with MPI. And then a few years ago, we said, oh, well, wait, we don't really care about MPI. Now we care about OpenMP. So there's different optimizations we have to worry about in the implementation of UPC. They're competitive in some cases. And in fact, I think when we just look at UPC versus OpenMP, they're very close to getting the same performance right now. I think that we should be able to do better in UPC because of the memory affinity that you get. But so far, we're really not seeing those performance advantages at the moment. And, but the other thing I've come to realize is even if you have UPC running globally across your machine, you're probably going to write a somewhat different algorithm inside the shared memory space in UPC than the algorithm you're going to use between the nodes which is for distributed memory, which also can be written in UPC. Because you'll make explicit copies of data that's remote across the machine, and you'll share it when it's not. And so you still may want kind of a hybrid programming style in UPC, even if all the code is written in UPC. Yes?
So if you combine OpenMP and MPI together, right, how hard is it, first of all, to do? I'm not sure I've never done it, right? But those two sort of languages I kind of know.
Yes.
Instead of learning.
You want to talk into that? Okay. I can repeat the question, yeah.
Oh, hi. Yeah, so the question is, so I'm familiar with MPI and OpenMP, right? So maybe it is just easier to combine them both in a hybrid model that you described instead of learning a new language like UPC. I've never done it before, but from your experience, how hard it is to implement and how does it compare to UPC?
Right.
Thanks.
So I think it's not too hard. We will certainly be advocating mixed MPI and OpenMP on the Hopper system as probably the best way to get memory scalability and also to get reasonable performance out of your code. And we've done some studies on this. So memory really drops if you use more OpenMP and less MPI in your parallelism. That's a very dramatic increase. I think it's actually not too hard to do. The subtleties come up with exactly how you're communicating. Like each OpenMP thread in most OpenMP implementations cannot send MPI messages. You send MPI messages kind of outside of the OpenMP stuff. And so now there's questions about whether that's the best way to use the network and how that's going to perform. But I don't think it's actually too hard. I mean, at the basic level, you've got your MPI application, and then you go through your loops and you kind of put the OpenMP annotations into it. And then you hope the implementations are all doing the right thing. Yes. Is there another? Oh, yes.
This is again to do with MPI's UPC difference. So one of the things which so one of the things was you avoid the copy
Right.
when you do the UPC. But does that bring in buffers being committed for a long time in the remote thread? And that can cause cache problems, like you have to that memory cannot be used for caching, for example. So you'll probably end up with more cache misses and stuff. So there is a penalty there, I guess.
Right. Well, let's see.
so how
So
does that
the question is really about whether you're tying up memory in the UPC implementation. And the way to think of it is, at least for put and get messages, the simplest kind of puts and gets operations, you are directly writing into the user's data structure. And that is the same data that you want to eventually go into the cache when they're computing on it. And so it's not tying up separate memory. It's just, I mean, what you do have to do in a UPC application is you have to keep track of the synchronization, because if you're going to write into some other processor's data structure, they better be aware of the fact that at some point a write can be coming through and not be looking at that data structure for a period of time. So separately, you have to then worry about when is that data structure, which is not a buffer, it's an actual array or whatever, when has that array been filled in, and when is it possibly in a somewhat corrupt state because the update is incomplete. So I don't think we have the problem with kind of the buffer management. In some sense, you've pushed it up to the application programmer, because those data structures are now user data structures. And so if you're trying to compute on a data structure and other processor is going to update it from a previous computation, those can't happen at the same time. So then you might end up making two copies of it and say, here's the one that you write into, here's the one I'll compute on right now. When you're done writing, I'll switch over and use the other one. But it shouldn't. So in cache pollution, maybe we can talk offline, because I'm not sure that I see the problem there either. But there may be. I mean, certainly the caches are complicated, and how they interact with the network interfaces is another. Actually, one of the problems of the MPI one-sided spec was because some networks on some machines are not cache coherent with the cache on the processor. So the problem is, if you do a one-sided operation, it comes into the network interface and gets, say, written into memory. If that cache has a copy of it and it didn't get invalidated, then it doesn't run. And so the companies involved in the MPI spec said, well, I don't want to support that. So we're not going to put in a one-sided communication mechanism that works, that doesn't work on my machine. So NEC is the example of a machine that's not cache coherent. And there was another one, but that machine doesn't exist anymore. And so PGAS languages don't really deal with that problem. They say your network interface has to understand the memory space if it's going to write directly into it. It has to be coherent with the cache. It's not globally cache coherent across the machine, but the network interface and the cache have to be coherent.
Thanks.
We're probably out of time. Okay, so thanks very much. And as I said, I'm happy to answer questions.